Okay, so elements have protons, neutrons, electrons inside them. We have to have this clear picture in our head of the nucleus that has most of the mass inside it with all the positive charge. And outside of that nucleus, there's an electron cloud. If you look at slides 11 and 12, all right, in your chapter 2 PowerPoint, you'll see some information about atoms that we talked about in the last slide. Again, I like to kind of do this at the beginning of these videos just to remind you to go back and review some concepts from before to make sure that you get it. Look at the images that are here, make sure you can explain them, make sure they fit with your understanding of how atoms look, okay? What we didn't get to talk about in the last video is a very important concept called atomic mass. This is not the mass number, and this is a big important point here that some students get hung up on. The mass number, which was A in our last video, is the number of protons and neutrons, all right? Atomic mass is not what we're talking about here, okay? Essentially, if I have a big chunk of, let's say, carbon, all right? So here's my big chunk of carbon, right? Some of this carbon is carbon 12, and some of this carbon is carbon 13. A very small part of this big chunk of carbon might also be carbon 14. So when I talk about the mass of this carbon, well, it's comprised of species that each have their own mass, right? Carbon 13 has an extra neutron relative to carbon 12. Carbon 14 has 2 extra neutrons relative to carbon 12. So what do I do about this big chunk of carbon that I could put on the scale in terms of accounting for all these different masses? That's where atomic mass comes into play, right? Atomic mass takes advantage of or accounts for the idea that isotopes exist, okay? What we do with atomic mass is we create a weighted average, and it's based off of all naturally occurring isotopes, and we do a weighting average of their mass. So if most of carbon is carbon 12, which happens to be the case, okay, then we expect the atomic mass of carbon to be somewhere near 12, but it happens to be a little bit more than 12. And that's because a small percentage of this chunk will be carbon 13 or carbon 14. And in fact, you can find the atomic mass on the periodic table, right? In our next video, we'll deal with a lot more information on the periodic table, but what you'll see for carbon on the periodic table is underneath it, there's a 12.01, okay? This is the atomic mass. The number with a decimal point on the periodic table is this weighted average. Now, is it 12? Nope, it's 12.01, which means there's a bit of carbon 13 and 14 that are making it a bit higher, right? The atomic mass is based off of a scale where we define an AMU. AMU stands for atomic mass unit. It's 1/12 the mass of a carbon 12. That's our standard. 1/12 of that mass of carbon 12 we say is 1 AMU, and then we base, all right, our entire discussion on these numbers on the periodic table using a weighted average on this atomic mass unit scale, okay? Chem 101 and the problems that you'll see inside Chem 101 use this approximation, right? It turns out that 1 proton is about 1 AMU. Notice I'm not saying equal, I'm saying kind of equal to or about equal to. And 1 neutron is about 1 AMU. A neutron is actually slightly heavier than a proton, so this definitely is an approximation, but the example problem will do, because it's how Chem 101 does the problems, uses this approximation, right? Whenever we're trying to calculate atomic mass, what does a weighted average look like? It looks like this equation at the bottom. So whenever you're asked to calculate atomic mass, this is the equation that you go to. I'm just going to explain this equation, and then the actual use of this equation is easiest to sort of enact and understand through an example that we could do together, okay? So, all right, atomic mass is equal to a sum. So whenever we see a big sigma with an I underneath, this I is an index, and this means that we're going to make a sum. We're going to have a bunch of things that we're putting together and we're adding. So what are we adding together to make our atomic mass? We take the percent abundance and we multiply by the mass. So these I's, these are the different isotopes, okay? So for each isotope, you find its percent abundance, you find its mass, you multiply them, and then you add the next isotope's percent abundance times its mass, plus the next abundance plus times its its mass. So that's what I mean, like this interprets to, oh, I find each isotope, percent abundance times mass, percent abundance times mass, percent abundance times mass, and I add them all together, okay? So most people are familiar with summation notation, but you might not have seen it for a bit. So as I just mentioned, the easiest thing to do when we're talking about atomic mass, and this is something that shows up in the periodic table, so it's really, really important in terms of understanding conceptually. We're going to do an example problem together, okay? So it's the easiest way to kind of elucidate what that symbolism means, right? So here's our example, right? We're going to be looking at chlorine, and we're going to be given some information about chlorine. And we're going to be saying, okay, so there's two types of chlorine, right? Chlorine 35 and chlorine 37. Now, you might even see chlorine represented like this, okay? When we kind of get lazy about writing atomic symbols, it's because, do I know what the actual proton number is for chlorine? Well, yeah, it's fixed. No matter what, chlorine has 17 protons. And if it didn't have 17 protons, it wouldn't be chlorine. So sometimes we even let that off of our actual writing, and we just say chlorine 35 and chlorine 37, okay? But for this instance, I'm just going to put it there, but realize it really doesn't need to be there, all right, to know that we have chlorine, right? It turns out that chlorine 35 is 75.8% of all chlorine. This particular isotope is about 3/4 of all chlorine, all right? This isotope is 24.2%, okay? Chlorine 37 is 24.2%, chlorine 35 is 75.8%. If I add these guys together, what do I get? I get 100%, so that makes sense. We're accounting for all the isotopes. So what we have here is a sum that we're going to have to create to calculate the atomic mass. Now for this problem, and this is a Chem 101 style problem, you're not given this isotope mass. This isotope mass and this isotope mass, they're actually something we can determine. We can get a value in terms of AMU out without using an approximation. But let's pretend that we didn't have a method of actually getting that. Let's use the approximation from Chem 101. We still have the same setup whether we're using the actual Chem 101 approximation or not. The atomic mass is a sum, and it's a percent abundance times a mass plus a percent abundance times a mass. So symbolically, I need to find the percent abundance of Cl35. I have to multiply it by the mass of Cl35. That is inside a sum, so then I'm also going to add to that the percent abundance of Cl37 times the mass of Cl37. And if there were more isotopes, we would keep going with plus ... But remember what we said above, there are only two isotopes here. That's the only bit of information. So this is how we interpret that summation notation. So it might look confusing. The bottom of the last sort of thing that we wrote down here before we erased, it might look confusing in terms of the symbolism, but this is what it interprets to. So hopefully you can kind of see now what that symbolically means, okay? So now let's use, all right, the Chem 101 approximation for this, and let's calculate the atomic mass. Are we given a percent abundance of Cl35? Yes, we are, all right? The percent abundance of Cl35 is given as 75.8%. Now, what we do is we turn that to its decimal. So I'm going to write this as 0.758, okay? So this percent abundance, you use the decimal form, right? Now, what's the mass of a Cl35? Well, again, that's something that we could get from an experiment, but in this case, oh, and also, these come from experiments. That'll be important as we do our analysis. Just keep that in the back of your mind, right? But if we don't have an experiment that tells us this mass, we can approximate that mass, right? If each proton and each neutron is about 1 AMU, then this guy right here, right, we're going to write as 35 AMU. That's the mass of a Cl35. It's not really the mass of a Cl35, it's about the mass of a Cl35. This came from a measurement, but this we introduced ourselves. This came from an approximation. So when we do significant figures, we have to realize that this is the measurement value. This is what's going to help us determine the correct number of significant figures in our work. Okay. Notice I included the unit AMU here. Now, are we given a percent abundance of CL37? Yep. 0.242. I'm going to use the decimal form. This is multiplying the mass of CL37. 37 AMU is a decent enough approximation in this case. So hopefully you can see the setup now, and now we can go through enacting the mathematics and calculating the atomic mass for chlorine, okay? Remember how we do math? We look at significant figures, and when do we round? Only at the end, okay? So our measurements, the things that we didn't introduce ourselves, but our measurements are going to determine the significant figures. What's the first step here? I have to take 0.758 and multiply it by 35. And what I get out in my calculator is 26.53. The AMU comes along as a unit. I just did some math. What am I going to check? I'm going to check significant figures. This, we're not pretending came from a measurement at all. It didn't come from a measurement, so significant figures don't matter here. It's almost like it's exact, right? We're going to stay with our measurement. 0.758 has 3 significant digits. These percent abundances, they need to be determined through experimentation, right? Do I get rid of this 3 now? Do I round now? Nope, we round at the end. What about this second step here? 0.242 times 37. I plug this into my calculator. I know I have to eventually add it to my 26.53, but the number I get out is 8.954 AMU. This again, for all the same arguments that we had before, would have 3 significant figures. This is the measurement. That's what determines the unknown value or the unknown error inside that number that we're now manipulating. The measurement determines that there's going to be 3 total significant figures because I am doing multiplication, right? Now I can take these 2 unrounded numbers and I can plug them into my calculator. And what my calculator gives me as an answer for the atomic mass is a value, and again, as always, please check my work, 35, right, 0.484 AMU, 35.484 AMU. Now, if I plug this into Chem 101, it'll probably yell at me because I am not using correct significant figures. This last step is addition. This number is good to the first place to the right of the decimal. This number is good to 2 places to the right of the decimal. So this number here, after this addition step, right, and that's why decimal place matters after this addition step, would be limited to 1 place past the decimal. So really, even though this is what my calculator spits out, this would be, all right, the correct number of significant figures. So what I input into Chem 101 is 35.5 AMU. And that is an approximation for the atomic mass of chlorine, taking advantage of its 2 naturally occurring isotopes. Now, if you look on the actual periodic table, the one that we're using in class, the one that's in D2L, and that's also in the slideshow in chapter 2, what you'll see underneath CL is 35.45. So you see that this gets us pretty close to this answer. This must have came from better measurements that we had, and actually probably came from no approximations being used, okay? This would round to 35.5 if it was only good to that place. So we see that we're kind of in the ballpark, and I think that's why Chem 101 uses this approximation, right? So if you're given a problem and you only have these percent abundances given to you, use this approximation like we did with this problem. The A becomes the AMU. The mass number becomes the AMU, and you can still carry out the calculation and get something that's close, right? I will mention one other thing I'd like you to do. In the slideshow that I gave you, there is information given about silicon, right? So if you look at let me check my notes here. Slide 13, you'll see information about silicon, and there's actually 3 different isotopes. You use the same formula and the same ideas. Now, you're not going to do the approximation like we did with this last example. You're actually given the isotope masses and their percent abundance. You're given everything. You don't need to use an approximation. You should be able to do that problem, and based off the information that you're given, what you should get out for the atomic mass of silicon is you should get 28.0855 AMU. And when you pay attention to significant figures, it actually goes out to that second decimal place so that the final answer is 28.09 AMU. So the reason I bring this up is because it's good extra practice. You can calculate the atomic mass of silicon given information about its 3 isotopes. You're given the masses and you're given the percent abundances. You put them into that formula and you should get out, if you do the math correctly, 28.09 AMU, right? We've been referencing the periodic table, and that's actually what the next video is going to sort of get into, is actually looking at the periodic table, understanding some things about it, and getting some information out that helps us then talk about chemical bonding.